Hi, this is Mr. Forster, and this is the last of our videos for the distance learning for the 2019-2020 school year. And a pretty simple lesson for the last week. It's kind of important, but just listen up. It's about functions and scatter plots. So let's talk about that. On the Khan Academy, however, there is lessons on two-way frequency tables. I'm not going to be talking about that, but Khan Academy does a good job of explaining it, and I don't think there are questions about functions, so please do pay attention when we go over functions. So here we go. So a function is a relation between two variables. Is it a function? And so we've seen linear functions, y equals mx plus b. We spent most of the year doing that. We've seen quadratic functions where quadrado, that means squared, x squared and negative x squared. If you remember, I called that Perry and Patrick parabola. That's a Perry parabola, and that's Patrick parabola. And we have also seen, there are also other quadratic functions, exponential functions, trigonometric functions, which are like a sine wave or a wave. But what is a function, and how do you know if a relation between two variables is a function? So the definition of a function, which is not that helpful to me, is a function is a relation between two variables such that each input has a unique output. The input is x and the output is y. Well, that doesn't help me much. So a little confusing is what it says underneath there. So let's see if we can figure out what a function is by example. So here are examples, by the way, of linear. There's a linear function, quadratic functions, exponential functions, trigonometric functions. And so those are all functions. What makes them functions, and how do we know what a function is? So is a relation a function in a table? So let's start with that. And let's think of people and places or a candy machine. So these are people and these are places. So, or we could think of a candy machine and push button 0, 1, 2, 3, or 4. So let's look at this first one. And so, of course, people cannot be two places at the same time. In a candy machine, if you push the number 0 and you want a Kit Kat, you better get a Kit Kat every time you get that. So here, on this, we have people 0, 1, 2, 3, and 4, and they're all going to different places. Is that okay for them to do that? Is that a function? And the answer is yes, it is. Think of a candy machine. 0 is a Kit Kat, 1 is a Snickers, 2 a Milky Way, 3 a Reese's, 4 Hershey's. And so all of the buttons that you push here give you distinct candy bars, and so that is a function. And so let's look at the next example here, this next T-chart. Is that a function? Well, what I notice here is I see the 3, 7. So think of these 3 people right here. That's Billy, Bobby, and Joey Gomez. And they're all going to the same place. They're all in the same family. Is that okay? Is that a function? The answer is yes. These 3 different inputs can have the same output, but we can't have different outputs for the same input. That's where it gets confusing. So think of a candy machine. Here, push 2, you get a Kit Kat. 3, you get a Kit Kat. 4, you get a Kit Kat. Do the candy machine have oftentimes more than one row of Kit Kat? And the answer is yes, because Kit Kat's a popular candy. So that is a function. Let's look at this one here. Here we have people going to places. Now look at this. Ooh, this is a function because even though this input is repeated, they are going to the same place. So this person 2 is going to the same place here. Or we could say push 2 and got a Kit Kat, push 2 and got another Kit Kat. Oh yeah, that's good. All right, so that is yes, a function. Well, let's look at here. Let's particularly look here at these 2 inputs, and they give different outputs. So this person says they're in Santa Barbara, and this person says at the same time they're in Santa Paula. And of course that can't be true. If you push 2 and get a Kit Kat and then push 2 again and get a Milky Way, you're disappointed. So that is not a function. And so what is a strategy? Look for repeated inputs right here, repeated inputs. And if there is a repeated input, then the output must be the same. So here we had repeated inputs, but the output was the same. Here we had repeated inputs, the output was not the same. So yes, a function, no repeated inputs. Yes, a function, 3 people going to the same place. Repeated inputs, but the output's the same. Repeated inputs, outputs are different. This is not a function. No. All right, next question. How about is the relation of function on a graph? This is a pretty fun one. A vertical line test. A vertical line touches the graph of a function at only one point at a time. So here's a line. This is our graph, y equals mx plus b. And this vertical line touches that line at only one place. If we thought here, okay, 1, 1, 1, 1, 1. So it only touches it at one place. And here, this vertical line on this parabola, although it touches it at an kind of an angle, it only touches at one point at a time. So that is, these are both yes functions. Here is where we have a problem. We have a sideways parabola where a vertical line touches the graph of this function at 2 places, and so it's not a function. This is not a function because a vertical line test can only touch at one point at a time. And so not a function. Let's go look at some more examples. Is this a function? Is this a function? And so here's our vertical line, and I see it touches once there. Does it touch more than once anyplace else? And the answer is no, so that would be yes, a function. Is this a function? Here I see it touches once, once, once. Uh-oh, here it touches 3 times. And so that is not a function. You can think of any time the line doubles back on itself, not going to be a function. Here, the circle, of course that's a function, right? It's not a function because the vertical line touches it twice. In fact, computers oftentimes graph circles with a half a circle on top and a half a circle on bottom because computers get confused about this because it's not a function. How about a vertical line? Well, actually, a vertical line is the only line that is not a function because 1, 2, 3, 4. In fact, a vertical line touches itself a million different, infinite number of places. How about this just scatter of points there? Is that a function? Well, this vertical line doesn't touch 2 points, so it is. And how about this here, these points? Whenever we have 2 points, and here we have 2 points, 3 different places, that is not a function. Yes, no, yes, no, and no. So I hope you understand how to see a graph of a function, whether it's a function from a graph. All right, is a relation a function from points? And so this can be a little, do these points represent a function? And it's a little confusing to look at this. 1, 5, 6, 9, 7, 5. Ooh, there's 2 5s. You might say, no, that's not a function. And I find this confusing to look at this, so I'm going to offer you 2 strategies. Put it in a table or put it in a graph and use the vertical line test. So here in the table, I do not see any repeated inputs. I do see repeated outputs, but that's the Kit Kat with 2 rows of candy explanation, or 2 people going from the same family going to the same place. So that is, yes, a function. Do these points represent a function? Again, it's hard to see looking this way. I recommend you put it in a table. And here we see the 2. It's kind of covered up on the toolbar there, but we see the 2 and the 2 giving different outputs. Here we see it visually. The vertical line touches those 2 points. And so that is not a function. Okay, and here's a good question. What point must be in the blank so that the relation is a function? So I did this to confuse you a little bit. 4, 5, 6, 7, 9, 5. Well, let's look at the outputs. 2, 3, 4, 5, 6, 7. You might say, oh, that's going to be 7. 2, 3, 4, 5, 6, 7. But then you have to look here. Wait a minute. Mr. Forster put another 5 there. And so we have to look at this 3. The input of 5 gave an output of 3. That 3 has to go right there. So since the input value resulted in a 3 in the second parentheses, then the blank must be a 3 because the input is a 5. So that's a 5. That has to be a 3. And so there's our 3. All right, so that's a tricky question. So you might put that in a table also, but you wanted to look to see that the inputs are the same, so don't be tricked by the pattern. The pattern doesn't necessarily matter. Okay, function application, a simple example. So, and this is an example of when you would need to know if something's a function. A computer can only process and evaluate data that represents functions. So explain why the following input can be processed or cannot be processed by a computer. Is the data a function? So here we have hours and temperature. So 5 a.m., 10 a.m., 12 a.m., 2 p.m., and 5. And we have all different times. But if you notice here, 5 a.m. and 5 a.m., it looks like somebody input this a.m. incorrectly. And since there are two different outputs for 5 a.m., this is not a function. And this is one of the reasons that the military uses a military time. That would be add 12 to that. That'd be 1,400 hours. And that, assuming that's 5 p.m., that would be 1,700 hours, or 12 plus 5, 17. So, but the way it is now, because 5 a.m., 5 a.m., it is not a function. It looks like there's been a mistake there, though. And so what about this? The date and the sales. So the 3rd, the 4th, the 5th, and the 6th. Well, we see these repeated outputs, but again, there is no repeated inputs. So on the date, the 3rd, you had $80 worth of sales, and of course, you can have $80 worth of sales on the 6th. So that is, yes, a function. And so look for repeated inputs. Don't worry about repeated outputs. Let's go on here. So that's function. So let's talk about scatter plots. Scatter plots, an association or correlation. You might hear association. You might hear someone say correlation. Association is used more commonly nowadays. Correlation is more old school. And making a prediction or a projection using a trend line or line of best fit. So scatter plots are real-life data, and they're plotted to see if the graph of the points form a pattern or a linear or exponential. So data in real life doesn't follow a perfect line. And so scatter plots are real-life data, and we can expect them to not necessarily follow a perfect line. And the pattern, that's supposed to say pattern, if any, of the graph of two variables, years versus population, shows us if there's an association or a correlation. So the graph, we could see, oh, it's going up and down, or it's going up, or it's going down. And if there is an association, we can make decisions based on the data or make predictions by extending the pattern or writing an equation. So we're using a lot of our tools that we learned this year on y equals mx plus b. So scatter plot, real life data, and it's not going to make a perfect line, but we're going to deal with that. So let's look at this. Here's positive association. We see these points, and this is the best we could do, where scatter plot, and these points, there's a line that kind of goes through the middle of there, and that's called the line of best fit or trend line. And so since this line goes uphill from left to right, this is called positive association. Just think of positive slope. These points that are far away from the line or the trend line, they're lay outside the trend of the other data points, they're called outliers. And so here we have GPA in hours study. As the hours study increases, the GPA increases. However, this person has a lot of hours studying and a medium GPA, and this person has the low hours studying and a high GPA. So they're outliers, however, because most people are studying more, their GPA goes up, and if they don't, then their GPA is lower. So this is an important sentence that you always want to use in scatter plots. As the units of x increases, the unit of y does what? Does it increase or decrease? In this case, the units of x increase. The units of y also increase in addition to that. So that's so we see these arrows up and up. And so as the hours of studying increases, the GPA increases. That's positive association. When both of the variables are going up, that's positive association. Here's negative association. Think of negative slope. So GPA and hours playing video games. As you play more video games, your GPA goes down. And so here we have somebody that plays very little video games but has a lowish GPA. And here's somebody that maybe they're doing something else, I don't know. But here's somebody that plays a lot of video games and has a pretty high GPA. And those are, again, outliers. As the hours of playing video games increases, the GPA decreases. And that's called negative association. As X increases, Y decreases. So as this goes higher, this number here, when it's low here, that's a high number up there. When it's high over here, that's a low number in Y. And so negative association does not mean that it's bad. It means that the line is going downhill. And in other words, it means that while the X is always going up, in this case, the Y is going down. Another example that'll show you that it's not means bad. As hours of exercising increases, your resting heart rate decreases. That's called getting in shape. This is a good thing, but it is also negative association. We see the exercise increases, the heart rate, resting heart rate decreases. So that's negative association or negative slope. And zero association. So your age versus your body temperature. Well, your age, as you get older, your body temperature should remain 98.6, unless you're sick, of course. So here we have body temperature. Some people run a little hot or a little cold, but 98.6 is the normal body temperature. And so there's really no information that can be gotten from this. This is zero association. Of course, if your number's way up here, you are an outlier and you're probably sick. And so as age increases, body temperature remains the same. That's zero association. Think of zero slope. Next, no association. Random points with no pattern. Height versus GPA. So I always like to say when I'm in class, all those people that are tall people, raise your hand if you think you're smarter. And so the tall people will raise their hand, of course. But of course there are tall people that have a low GPA, and there's or just low GPA. That doesn't mean they're not smart. And there's short people that have a high GPA, and short people, and everywhere in between. So as height increases from left to right here, there is no association between GPA. There is no line or pattern here. We couldn't really put a line anywhere. So we call that no association. And so here's an example, quick example of nonlinear association. We see this a number of sick people over time. So a lot of times illnesses can be diseases experience exponential growth. And so we can see here that these points do not follow a linear trend, but they are showing a trend, and it's nonlinear. And of course, you wouldn't want to put a linear model for something that's nonlinear. And so exponential growth and this idea of exponential growth for illnesses is when we have to be very careful when the spread of diseases. So because it may look like it's growing very slowly, but then it starts to take off. So, but do not just exponential growth. Just know that it exists, and you don't have to worry about modeling it now. You'll learn that in high school. And so, line of best fit, a very important point idea. We have a scatter plot here, and we put a line of best fit. It doesn't have to touch any of the points. It just kind of goes through the center of them, and you can eyeball it. In later years, you'll find a mathematical way to put the line of best fit. But we're going to talk about modeling, reading data, and making projections. So first, if we see a linear pattern, we can place a line of best fit. So we've done that here. We see a linear pattern, we put the line of best fit. And it's also called a trend line to fit the data. Next, we can find the equation of this trend line in slope-intercept form. And here we know it's positive slope, and it has not a zero y-intercept, but a low y-intercept. So we don't have numbers here that will give us a real idea on what it is, but I guess we could figure it out, but that's beyond what I'm talking about now. So we can evaluate the data by using the trend line, and that is so here, if you have a 2.0 GPA, Bingo, we come over here. How many hours of studying did you do? 1.5 hours of studying. What if you do 10 hours of studying, and what will your GPA be? And it says 3.8. And so these are just examples of using the trend line. So we'll go over here and then over to the line and down, or go over here and up to the line and over. I don't know if you remember, we did an activity at the beginning of the year with Newton's Revenge roller coaster, and we did the same thing here to find the height that it was safe and such. So, and last, after we look at the data and see what we can do with it, we can read the data. We can also make projections with the data for something that's way off here. I know that the point's going to be up here someplace. Of course, that's for somebody that has above a 4.0 GPA in this example. But let's look here. Using the equation of the trend line to make projections, that's called forecasting. And that's a good career. People do that for a living. So given the scatter plot, answer the following questions. And so we see that this is a negative slope, and we put the line of best fit in there. And I would have put it a little bit higher actually here. But as the units produced increases, the cost decreases, cost per unit. So we found the starting value, which is 25, and this is down one. For each unit produced, it goes $1 cheaper, I guess. So the -1 is the slope, and so there's the equation of the trend line. And that's important to be able to do that. And now here's a question. Let's use the trend line. If you produce 15 units, what is the cost per unit? Well, I guess we don't have many units, we don't have any numbers over here, but we'd say 15 over here, and then we'd go down here, how many units? But we're going to use this equation of the trend line. So 15 units, that's x. So we're going to say x equals 15, and I'm going to write my equation, and then I'm going to substitute 15 into the place for x, and I'll multiply -1 times 15, and I'll add those together, different signs, subtract, and I get 10. And so 10 what? That's y equals 10. So that's cost per unit is 10. So the cost per unit is 10. So if we produce, 15 units over here, the cost per unit is 10. So that must be 15 comma 10. Oh, that's the point right there. So there it is. If you produce 15 units, the cost per unit is $10 each. And that's using our trend line. Let's do another example. What if I give you y, and I want to know what the cost per units is? So how many units did you produce? So if you want the cost per unit to be $5, how many units should you produce? And again, we've got this equation of the trend line from the graph, and now it's just algebra that we've learned before. We substitute 5 for y and subtract 25, and we get -20 equals -x, and divide by -1, and you get 20 units. So at 20 units, it's $5 per unit. And so that is using of the trend line. And so we're coming to the end here. There is an idea, concept I'd like you to know about, quantifying the degree of correlation or association. So we can put a number on it, and it's called the correlation coefficient or the association coefficient, and how good of the fit is of the data. And so that number goes between 0, which is no association, just scattered points, and 1.0, perfect association. So you might be doing a study on two different things to see how they're related. And of course, you're not going to get perfect association. But you'll learn about this correlation coefficient in later classes. But this correlation coefficient of 0.9 is a very strong correlation between whatever the two variables are. So 1.0 being perfect association or perfect correlation, that's very strong. If it's close to 0, not much association. And that we can talk about cause and effect, possibly being one being related to the other. So a closing comment. Today, with association, computers are able to do multivariable association. They can do graphs that are 3D. And this is the basis for advanced data analysis and artificial intelligence. Computers can analyze data and make decisions, and they can analyze many different variables at one time and see which ones are correlated And if there's a correlation, they can make decisions based on that. So it's important for us humans to remember that the concepts and let the machine do the work, but you should know how the concept works. And so we've seen, as a kind of a closing statement here, we have seen that numbers, data, can be tabulated, plotted on a graph, and the shape of the data allows us to write an equation, if there is a shape, to model the situation. And these models can be used to make educated guesses or decisions, and this is a very powerful use of math in real life. And so with that being said, that's the end of my video, the end of the last video, and I thank you, and it's been a pleasure being your teacher. Good evening. Mr. Forster signing off.